Out in the vacuum of space, the sky is a permanent black. Even in direct sunlight, without an atmosphere, the surrounding void remains dark. But here on Earth, that blackness is replaced by a bright, glowing blue canopy. Since our star emits purely white light, why does it create a vibrant blue ceiling instead of illuminating a dark void? The blue sky is the result of the atmosphere itself interacting with that light, intercepting it before it ever reaches our eyes. To understand that interaction, we have to scale down to the microscopic starting point, a single beam of sunlight. While we often perceive sunlight as yellow, it is actually a white-hot blend containing the entire visible color spectrum. This diagram shows how white light is composed of electromagnetic waves. Red light travels in a long, stretched-out pattern, with peaks spread far apart. At the other end, blue and violet light travel in much shorter, choppier waves, oscillating at a higher frequency. Color isn't a decorative trait. It is a physical measurement that dictates exactly how a wave interacts with the matter it hits. Before reaching the ground, those waves hit a dense barrier, Earth's atmosphere, which is packed with nitrogen and oxygen molecules. The long red and orange waves easily cruise past these tiny gas molecules without making contact. But when a short, choppy blue wave encounters a gas molecule, it crashes directly into it and ricochets in every direction. This is Rayleigh scattering. Blue light scatters 10 times more effectively than red light, ping-ponging through the atmosphere in a chaotic, overlapping web. It was Albert Einstein who finalized the exact mathematical formula for this in 1911, confirming that these molecular collisions were responsible for the effect. The daytime sky is effectively a glowing field of colliding shortwave light, a glow so intense that it hides the stars behind it. To understand the final color we see, we must move from the physics of the air to the biological receiver on the ground, the human eye. If shorter waves scatter more easily, and violet is even shorter than blue, why isn't the sky purple? It comes down to two filters. First, our sun naturally emits less violet light. Second, the color receptors in our retinas aren't as sensitive to those specific frequencies. This graph maps the human eye's red, green, and blue cones. Our eyes have a dominant detection peak sitting squarely in the blue spectrum. As the brain processes these overlapping frequencies, the scattered light is perceived as a pale bluish-white blend rather than deep violet. The color of the sky is a joint venture, half atmospheric physics and half biological perception. This balance shifts as the sun drops toward the horizon. Light must travel a significantly longer path through the atmosphere. Blue waves scatter and dissipate entirely before reaching you. Only the long, undisturbed red and orange waves survive to hit your eye directly. A red sunset isn't a change in the sun's output. It is simply the visual result of missing all the blue light. We can test these variables by looking at a different planetary environment, Mars. The Martian atmosphere is thin and filled with iron-rich dust, which changes how light scatters compared to Earth. As this photo from the Martian surface shows, the daytime sky on Mars is a rusty, brownish orange. At dusk, the effect flips. Because of the specific size of the dust particles, a Martian sunset scatters the red light away and turns the sky around the sun blue. As we've seen, Earth's blue sky is an optical byproduct unique to our planet's specific recipe of air. To find out more about the physics of our world, subscribe to What Is Defined.